In this video, we'll look at solving for volumes of revolution using disks and washers. As you can see, what I've written down is the general formula for volume, which basically says the integral, or the sum of an area times its thickness, will be equal to the volume. And this could be said if its slices are perpendicular to the x-axis, or if slices are perpendicular to the y-axis, everything will just be in terms of y, and our limits of integration, c to d, are in terms of y also. The only other formula we need to look at is the general formula for the volume of a cylinder, which is volume equals pi r squared h. I've highlighted the h since really that's going to be our thickness, the dx or the dy that we'll be looking at. In our first example, we'll look at the area y equals x squared plus 3, the y-axis, the x-axis, and x equals 4, that bounded region, revolved about the x-axis. So let's sketch our graph first. We have x squared plus 3 will look something like this. We'll just do a quick sketch here. We have the y-axis coming down here. We have the x-axis coming across here. And then we'll just take the line x equals 4, which we'll say is about here. All right, and there we have 3. So we're looking at this little area right here. And then what we're going to say when we look at volumes of revolution is we're going to look at the idea of a dotted line I like to look at for what's going to be revolved, and it's revolved about the x-axis. So we can look at this entire shape, or what I prefer to do is look at one slice. And in looking at one slice, let's say this piece right here, when this comes around, it'll rotate around, and I'm just going to stop halfway, and it's going to form a half a disc. If I was to continue around, we would see the full disc here. So let me pull that piece out. I'll just show you this other. If we look at the end, we'll have the same result. So it doesn't matter where you take your slice, you should end up really with the same type of picture. So let's pull that picture over here and just see what it is we're actually looking at. So here's the disc, which is really just a cylinder. This is our slice. And what I want you to really notice, I want you to focus on when we sliced it, our thickness was dx. That tells me everything is in terms of x, and that's what we're going to look at in this video. And our axis of rotation, we'll say cut through here and was coming around. So the only thing we need to identify is the radius, and we already have the height as delta x. You can see the radius is going to be the length from the center to the outer edge, which is really just how far we're going up to our function. So you'll see that the radius is equal to the y value, or in this case, x squared plus 3. We see our height is equal to the thickness. I'm saying dx, the way I drew the picture, it's delta x. We'll just go with dx for that infinitesimally thin slice. So now we can say that our volume, or we really have a piece of the volume here, so we can say we have dV is equal to pi r squared h. In this case, our dV is going to be equal to pi. Our radius is x squared plus 3, so we have x squared plus 3 squared. And remember, our height is really just dx. It's our thickness. So when we go and we really look at the formula, it's the volume is going to look at the integral from our bounds, which is from the beginning, which is 0, and we said up to 4. So from 0 to 4 of pi times our radius squared, so that's x squared plus 3 squared, times our height, which is just dx. We can clean this up a little bit, and we can just write this as v equals pi times the integral from 0 to 4 of our radius squared, x squared plus 3 squared, dx. From here, we can either use a graphing calculator program to solve for this or some other algorithm, or we can try to take a quick look at this by hand and just use basic integration techniques. Before we can integrate this, you'll recognize we need to simplify this. So if we were to expand this, we'd have x to the 4th plus 6x squared plus 9. And in integrating that, we will still have pi, and that will be of 1/5 x to the 5th plus we'd have 6 over 3, because we're raising it to the third power, and we can simplify that, plus 9x, and then that would be evaluated from 0 to 4. And in doing that, you'll find you'll get a value of 368.8 pi, which is approximately 1,158.6193. In our next example, we'll look at a very similar problem, but now we have a generalized approach. We're going to look at y equals root x bounded by the y-axis, the x-axis, x equals 9, and we'll revolve it about the line y equals 2. So it's no longer just the axis. But what I want to point out to you is really we just have a general formula that says v equals pi, the integral from a to b of whatever our radius is, and we're keeping this in terms of x squared dx. This is the idea of a disk. But what we're going to notice in this example is that there's a gap. We're going to have to modify this slightly and look at the idea of a washer. So let's take a look. So y equals root x. We'll do our general shape right here. Looks something like that. And it's bounded by the y-axis, which really doesn't seem to have an impact on here. We have the x-axis, and we have the line x equals 9, which I'll put here. So let's shade that area in. And this is going to be revolved about the line y equals -2. So here's y equals -2, and it's going to be revolved about there. So let's go ahead and take a look at what our slice is. So I like to slice in the middle. And when we revolve this about the line y equals -2, you're going to notice when it spins around, there's going to be a gap. And I'm going to stop halfway again. It's easier for me to visualize. And I'll stop halfway again. And this halfway stoppage lets me see my radius a little more clearly in both. So let's pull that out and see what it would look like if I drew the full cylinder. So it would have looked something like this. And it would have been revolved about this line right here, coming through here, y equals 2. And what you'll notice is that there's a hole, more or less, in here, inside of there. So in looking at that, we just need to identify each radius. So there'll be an outer radius, which is simply our line going from the axis of rotation to the function itself on the outside. And the inner radius is going to be the inner part of our shell right here. So when we look at it here, we can see our inner radius is the whole part, and then our outer radius goes to the edge. So what I like to write down is for the outer radius, I like to use an uppercase R sub 0 and identify what that length is. And since it's revolved about y equals -2, there's an extra little space there of 2 from here to here before we begin. So we can say it's 2 plus y, or in our case, the y value is root x, 2 plus root x. Our inner radius, I like to use lowercase r sub I, is really just the distance from our axis of rotation up until the x-axis, which in this case is simply just 2. So our piece of the volume here, dV, is going to be the outer cylinder minus the inner cylinder, which we can combine. We can factor out the pi, and then we have r outer squared minus r inner squared times our thickness. And remember, our thickness again is dx because our slice was perpendicular to the x-axis. So in looking at as a full integral, we would have volume equals pi. That can be factored out as a constant. And we're integrating from 0 to 9 because that's where all of our slices would have been. And you can draw, again, a slice anywhere. And our outer radius is 2 plus root x quantity squared minus our 2 squared dx. And we'll take a look at that a little more clearly right over here. So let's rewrite that one more time. We have v equals pi, the integral from 0 to 9, and we'll have the quantity 2 plus root x. Just be careful where you put the squared. Sometimes they can get lost. And then we did have 2 squared, which I will simplify now as just 4 dx. So again, we can use a computer program to simplify this, or we can do this by hand. We can take a quick look at expanding this. We would need to expand this and simplify this, and you would end up in simplifying this to be 1 plus 2 root x plus x, and then we'd have minus 4. And all of this would again simplify simply to pi, the integral 0 to 2 of 2 root x plus x minus 3 dx. And if we use the power rule, we can finish integrating that. And so we can either do that by hand, or again, we can use a program. We would end up with 49.5 pi as our final answer. In our third example, we'll look at what happens when we revolve about a line that is above the bounded region. So I'm going to take a look at y equals e to the 1/2 x, which will just approximate to look something like this. The y-axis, which we have here, the line y equals 4, which we'll cut across here, and x equals 8, which will be this bound right here, 8. But it's going to be revolved around the line y equals 6, which I'll just throw in right here. And we'll shade in our region. So the only difference is the direction that we're going to be going. And we're going to have to be very careful with identifying the inner and outer radius. So again, I'm going to take my slice, and it's going to be perpendicular to the x-axis, but it's right here. Here we are in the middle of our shape. And again, it's revolving about the line y equals 6. So I'm just going to come across like this, and it would revolve around. And again, I just like to draw half of that washer shape. But again, you don't have to even worry about that. The only thing you're worried about is the ability to identify the outer radius and the inner radius. So in this case, I'm just going to go straight from my picture and look at a perpendicular distance from our axis of rotation to our slice, and again, the same thing to the outer edge of our slice. So we just have the inner edge of the slice and the outer edge of the slice. And then you'll notice that our distance to that axis of rotation to the x-axis was 6. So what we have for our outer radius is this total distance is 6, but we see this piece right here is what we're looking for. Going this way, this would just be the value of y, which was equal to e to the 1/2 x. So our difference is going to be 6 minus e to the 1/2 x. And we can also see our line here that was at 4. The distance from the 4 to the 6 is simply 2. Or again, we can use the idea that we go down 6 and then we're going up to 4. So we're really doing 6 minus 4, which in our case is just 2. And yet, when it's above, it'll always be a subtraction compared to the one you saw earlier, which was below, which was addition. So our slice volume will be equal to pi. It'll always be the outer radius squared minus the inner radius squared times the thickness. And again, our thickness of our slice was perpendicular to the x-axis, so it is dx. So our volume will simply be pi, the integral, and our slices are going across from 0 up until our limit of integration of 8, so we're going to go from 0 to 8. Our outer radius was identified as 6 minus e to the 1/2 x, that will be squared, minus our inner radius, which was 2, also squared, with our thickness of dx. Now again, we can simplify this and solve this by hand, or we can use a program to solve it. Let's write it out over here. If we were to simplify this, this would become v equals pi, integral from 0 to 8. And if we were to expand that, be careful with power rules, we would end up with 36 minus 12e to the 1/2 x plus e to the x, and there's our minus 4, and we can see how that simplifies a little bit more from 0 to 8, and that'll end up being 32 minus 12e to the 1/2 x plus e to the x dx. And if we want to continue doing this by hand, we would end up with pi times 32x, integrating 12e to the 1/2 x. It's still e to the 1/2 x, but we're going to have to divide by that 1/2, the idea of the u substitution or the idea of the chain rule. We'd have 24e to the 1/2 x, and the integral of e to the x, everybody's favorite, e to the x. And we'll evaluate that from 0 to 8, and in doing so, you end up with 19.49. You end up with 1949.6023, and that's continuous, and don't forget to multiply by pi. So we end up simplifying a little bit more, and we'd have 6,124.8563, and that would continue on forever. In our final example, we're going to look at what happens when we have an area bounded by two curves and revolved about another line. We'll look at this a little bit quicker. This one is really the same idea. So if we have y equals sine of x, which will look something like this, I'll start to sketch that out, bounded with y equals cosine of x, so it's going to come down to here, and then we have the y-axis. We see our bounded region. So you can see that you're going to have to solve for your point of integration here. We should recognize that that's pi over 4 where the two of those meet. If not, we can always solve for that. And this is going to be a revolved about the line y equals -2. And when we take our slice, we see it right here. So let's try to do this one without getting into a three-dimensional picture and just identifying what our different values are. So we should be able to see our inner radius goes from the axis of rotation up to our first curve. So I'll identify r sub I as that's a distance of 2 plus, and that's going to be sine of x. Our outer radius also goes up to the x-axis and then goes to our upper curve, which is cosine of x. So our outer radius is going to be 2 plus the cosine of x. And that's going to be revolved about the line y equals 2. And once you identify these, really you are all set. I do like to write down dv, what my little slice would have been. It would be pi, and then we'd have the outer radius, which is 2 plus the cosine of x, quantity squared, minus our inner radius, which is 2 plus the sine of x, quantity squared. And all that times our thickness. Again, our thickness is dx. So we don't need a fancy picture here, just some straight up geometry pictures. So our volume will be pi, the integral from 0 to pi over 4, our limits of integration, again, of our outer radius, 2 plus cosine of x, quantity squared, minus our inner radius, 2 plus sine of x squared dx. And then in simplifying this, we are going to have to expand it, and what will come in handy, and we can look at that in integration techniques later on if you'd like, we'll want to simplify using some trig identities. A trig identity that comes up that's handy in this case would be the fact that cosine squared of x minus the sine squared of x is equal to the cosine of 2x. That's just a little side note there if you're interested in doing this by hand. But when you end up solving this, it ends up being the volume is approximately 6.7759.